is our class on stochastic processes. What's the course code for this, if I may ask? Okay. So STA 4101. 01, right? Okay. So stochastic processes. Good. So that's the course title and that's the course code. What I'm going to be doing today basically is to make you appreciate the essence of the course, coming from both real life and the field of statistics. Is it clear? So basically, we are introducing ourselves to stochastic processes. Now, for us to do that, we have to answer several questions. Just the same way you would meet someone who you don't know or never knew before now, and would have to introduce yourself. If I tell you to introduce yourself to somebody, it would involve starting with your name, right? And beyond your name, you may start telling the person where you come from, by virtue probably your state of origin, your village, and you may go as far as telling the person what you do, and even go as far as telling the person what your nature is. Are you a calm person? Are you a quiet fellow? Are you an introvert or an extrovert? You may start telling the person certain things. But the essence of doing all those things embodied in one is to make the person know who you are. Do you understand me? In other words, introducing yourself to the person. Now, what we want to do today is to introduce stochastic processes. Is it clear? So I'm going to start firstly with this. Let me use this black marker. Okay, so let's start with the word. Let's isolate from stochastic processes as a topic. Let's move out that word, stochastic. Is it clear? So the word stochastic means random. Okay? You can interpret the word stochastic as what? Random. Is it clear? That will quickly tell you that if random as a word is a synonym of stochastic as another word, it means you could quickly put this in place of stochastic in the topic stochastic processes. And if you don't want to say stochastic processes, you may end up using the term random processes. Is it clear? So you won't be out of place to say random process as a replacement for what? Stochastic processes. Is it clear? So what I have just done is just like telling you my name. Okay? So stochastic processes could also be called random process. Let's call that story number 1. Now, if I ask you to define what a stochastic process rather is, you may stop there with saying a stochastic process is a random process. Is it clear? But the question now is a stochastic process the only random process? As such, the answer to that question will make you know that that definition has to go beyond defining it as a random process, because in your definition, you have to tell us the nature of this random process you call a stochastic process. Is it clear? So what type of random process is a stochastic process? So please, I would love us to adopt both dictating and writing at the same time. Is it clear? So let's start with defining a stochastic process. Let's put this down. So I'm going to clean this up. Let's put this down. So the word stochastic, is synonymous to the word random. Okay? I'm going to put a full stop there. In other words, one may calling a stochastic process. However, calling a stochastic process a random process does not clearly define exhaustively what a stochastic process is. You see it? So just because you can call a stochastic process a random process does not answer the question, what is a stochastic process? Okay? Statistically, a stochastic process is defined as a collection of random variables indexed, or let me use the word that are indexed, in a mathematical set. Usually interpreted as time. Okay, so again, we are going to put a pause there and then explain. Is it clear? There are certain things we need to know. So it is not just about the writing, about the definition. There are certain things we really need to explain. So we've moved from a breakdown of the word stochastic or the topic stochastic processes to its definition statistically, okay? Now, what I want us to do is to explain that definition. So if we say statistically, a stochastic process is defined as what? A collection of what? Random variables that are indexed in a mathematical set that is usually interpreted as what? Time. What then do we mean? What then do we mean? Okay? What do we mean? So are you done writing? If you are done writing, please put your pen down and let me explain. Now, do you recall sometime probably in your year 2, your 200 level or 300 level, that you must have gone through the definition of what was called a random variable? What did we define a random variable to be? Who remembers? Huh? Or should I remind you? Okay. Now, we have defined a random variable as a real valued function defined over a probability space. Okay? So, now the question is, what differentiates, if there is something called a random variable, I now add to that idea of a random variable. I now tell you, in addition to knowing what a random variable is, if I ask you, what is a stochastic, what can you call a stochastic random variable? Now, that will give rise to another question. What is the difference between a stochastic random variable and a random variable? Now, please, let's see something. You see, a random variable, if this is a random variable, let's say, for instance, this variable here represents observations. Observation probably in terms of the heights of students, or observation in terms of the weight of certain objects. Are you listening? Yes. Now, this observation may just be taken in one instance of time. Please listen and listen clearly. I asked them in my exam, I asked a question from the, I think, was it the final year class before you or your class? I asked one particular group to tell, okay, I think it's the now graduating class, right? I asked a question for them to clearly state the reason in an ANOVA process that gives rise to comparison of means. And the explanations, none of them, as far as I marked, gave me a satisfactory explanation, making me know clearly what gives rise to comparing means. You know, in an ANOVA process, you would often, whether it is a one-way ANOVA or a two-way ANOVA, you would often test the null hypothesis. Okay? And if it calls for a rejection, let's assume that there were three treatments or four treatments. You know, the null hypothesis will tell you that there is no significant difference in the treatment means, right? Now, and if it so happens that we have to reject the null hypothesis and then go with accepting or do not, as in not rejecting, what do you call it? The alternative. The question now is, when you say there is significant difference, the question is, this significant difference we have experienced, that the ANOVA is telling us, the test we performed is telling us, where is it coming from? The significant difference, is it between treatment 1 and treatment 2, treatment 1 and treatment 3, treatment 2 and treatment 3, or treatment 3 and treatment 4? Where is that difference coming from? And I was expecting the students to be able to clearly state what gives rise to comparing the means, but I couldn't really get that. Now, in this instance, I want you to be able to tell the difference between what can be regarded as a normal random variable and what can be regarded as a stochastic random variable. Is it clear? Now, a normal random variable, as we defined earlier, has a slight difference from this. Apart from the fact that for you to get this, a stochastic random variable, you would have to take a collection of these. So this is often gotten in an instance of time, such that I could come here. Let's assume that this is this space was like a farm where we planted certain let's say potatoes, and we harvested them and took the weights to know how they fared over a period of time at maturity. Now, if we call X the weight of potatoes harvested at that period, you will notice that if there were 10 of them harvested, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10. If there were 10 of them, you will notice that we would end up having X1, X2, X3, X4, X5, X6, X7, X8, X9, and what? X10 values, right? We have 10 values that this random variable will assume within that space of time. What if this, let's assume that this was taken in January. At the instance of the random variable, we don't consider this, we just consider the values assumed by this random variable at an instance of time. But what if we now want to consider this random variable monthly, such that we will consider the yield at the end of January, we will consider the yield again at the end of February, at the end of March, right? April, May, June, for a year. You would notice that you would now have this, the X1 you produce, the weight of a potato you pick from the 10 in January. If you can harvest again another 10 in February, this X1 will not be the same value you will get for X1 in February. It will not be the same value you will get for X1 in March, April, May, or what? June. As such, you will now notice that even though the random variable remains x, it is now changing per month. As such, you could call January, it is still capital X. You could call January rather, you could call January X1 as the first month, okay? The first time you've taken that measurement, you could now call what? February X2 as the second month. And it goes on X3, X4, up to what? X, it's not necessarily X10. You may have, let's say, Xn of them. This collection put together is what will make your what? The collection. Is it clear? As such, this collection of random variables is what we'll be referring to as what? A stochastic process. Okay? A stochastic process, and the variable will now be considered as a stochastic what? Random variable. Is it clear? Good. So, coming back to the definition, a stochastic process is defined as a collection of what? Random variables that are indexed in what? A mathematical set, usually interpreted as time. Okay, so moving on from that, let's now move over to the next thing that I want to say. Okay, so the next thing we want to see is this. How are stochastic processes classified? How are stochastic processes classified? Now, stochastic processes are classified using properties or considerations such as the index set of the stochastic process if you don't want to use the index set of the stochastic process to classify it, you could use what we call the state space of the stochastic process, or you could use a third measurement or a third yardstick to classify it, which is the dependence of the random variables in the stochastic process. Okay, so what usually gives rise? If I tell you to classify a stochastic process now, for you to classify the stochastic process, somebody cannot ask you to classify a stochastic process and you just jump into answering that question. I hope you understand what I'm saying. This is what I mean. Should I ask you now, what types of stochastic process are there? You will be wrong to give me an answer to that question immediately. Do you know why? You will be very wrong to give me an answer to that question. Because there are three ways to view a stochastic process for classification. So what I will be expecting, should I ask you that question? How can we classify, okay, what are the types of stochastic process or classes of stochastic processes? I would expect you to ask me, sir, what classification do you want? Do you want an index set classification of the stochastic process? Or do you want a state space classification of the stochastic process? Or do you want a dependence classification such that you can use the index set, you can look at the index set of a stochastic process and classify it based on that? Do you understand me? In that case, it will give rise to different types of what? Stochastic processes. If you don't want to use the index set, you could also be looking at the stochastic process from the angle of what? State space. Okay? And that would also prompt the way you classify the stochastic process. And if you don't want to use that, you may use what? Its dependence on what? The random variables. Okay? Now, so that's why we are saying that stochastic processes are classified using properties of what? Consideration of considerations such as what? Index set, right? Index set, or state space, or what? Dependence of the random variables in the stochastic process. So I can look at the stochastic process, and judging by how dependent on one another the variables in the stochastic process is. Remember, we have said here that a stochastic process is what? A collection of what? Random variables. So we can use, if these random variables in that collection are dependent on one another, it could give rise to a classification scheme for a stochastic process. Do you understand me? Then, another thing that could give rise to the classification of a stochastic process is if a stochastic process is xt. This t here is the index we are referring to, and this t is usually a subset of a space, or a set rather. It is usually a subset of a set. So I can say my t is a subset of R, the set of real numbers. I could say my t is a subset of what do you call it? Let me use okay, I could use 0 to 5. My t could be this. I could select my t. When we talk about the mathematical set, we are referring to sets like this. I could say my t is a subset of what? Of n, the set of all natural numbers. Do you understand me? So my t could take values from any of these sets, and based on how, or the nature of t, you could also classify what? A stochastic process. Is it clear? And a stochastic process could also take what? A state space. Do you understand me? And the state space could also determine how you classify a stochastic process. Is it clear, everybody? And that brings me to the next thing I want to discuss before we round up this class, this first part of our introduction. Now, the next thing I want to explain, please take note. We are going to be detailed in the next class, but the next thing I want to explain is this. Based on what we've said here, index set, state space, and what? Dependence of random variables, we'll be looking at these two. How to classify stochastic processes based on what? Index set and what? State space. Is it clear? So, using the index set as a means of classifying, a stochastic process gives rise to two classifications. Gives rise to two classifications of a stochastic what? Process. A stochastic process. Meaning that if you use the index set as a means for classifying stochastic process, it will give rise to what? Two classes of what? A stochastic process. So, using the index set as a means of classifying a stochastic process gives rise to two classifications of a stochastic process, namely, one, discrete time stochastic process, and two, continuous time stochastic process. Okay? I believe I can wipe this off, right? So the question now is, now that we know that you could use the index set of a stochastic process as a means, a property, or a consideration for classifying a stochastic process. And furthermore, we have now said that once you use the indexing of a stochastic process to classify it, especially when, take note, the indexing is interpreted as what? Time. In this case, our index is the parameter t, which is what? Time. It will give rise to two classifications of the stochastic process. This is when you are using what? Index. And in particular what? Time. Is it clear, everybody? Now, discrete time stochastic process and continuous time stochastic process. The question now is, when is a stochastic process a discrete time stochastic process? Okay, so we would say a stochastic process is called a discrete time stochastic process if its index t are values that are finite in nature or countable. Is it clear? So when the value of t is either finite or countable, it will give rise, that is if you are using t, the index, to classify a stochastic process, it will give rise to what? A discrete time stochastic process. So in other words, a stochastic process is called a discrete time stochastic process if its index t are all what? Values that are finite in nature or what? Countable. Then we would say, however, if the values of t are uncountable or taken within an interval of values, then we say the stochastic process is what? Continuous time. Is a continuous time stochastic what? Process. Is it clear, everybody? Okay, so let's do a quick recap of what I have said so far. So we started this introductory class with saying that stochastic means what? Random. And if stochastic means random, it means stochastic processes could be regarded as what? A random process. That was my first statement, right? Now, the second thing we've said in this class, in my second paragraph, of course, is the definition of a stochastic process. So what is a stochastic process? Since telling us that a stochastic process is a random process is not enough, what then is a stochastic process? We define it as a collection of what? Random variables that are indexed in what? In a mathematical set, usually interpreted as what? Time. Is it clear? Now, after that definition and the explanation, separating a stochastic random variable from just any random variable, we went on to discussing the classification measures for a stochastic process. Question is, how can you classify a stochastic process? For you to classify a stochastic process, you need to look at three angles to the problem. Am I classifying the stochastic process based on its indexing? Or am I classifying the stochastic process based on its state space? Or am I classifying the stochastic process based on the observation of dependency of what? The random variables in that collection. Okay? Now, where are we at this point in time in our discussion? We are now looking at how to classify a stochastic process using its index set. Now, in my next class with you guys, I'm going to explain in detail what I have not explained today. That is, what is the index set? We have to answer that question. What is the state space? We have to answer that question. But let's start with classifying a stochastic process using its index set. If you are to classify a stochastic process using its index set, there are two classifications of a stochastic process. Do you get me? It is either the stochastic process you get as a result of classifying it using its index set will give rise to what is called a discrete time stochastic process, or it will give rise to what is called a continuous time stochastic process. Now, question is, when do we have a stochastic process we call a discrete time? A discrete time stochastic process will result from a case where the t values in your indexing are what? Are discrete. That is, they are finite in nature or countable in nature. Is it clear? However, if it so happens that the t values in your indexing, note that we are interpreting t as what? Time. If the t values in your indexing are such that they are continuous in nature, or they are what? Uncountable in nature, then it will result in what is called a what? A continuous time stochastic process. So you don't just open your mouth to say a stochastic process is classified into two, this and that. No, the question is, from what angle are you classifying? Are you classifying from index, the index space, or index set, or are you classifying from what? The state space, or are you using their dependency properties to what? To classify? Those are the three questions, but we shall consider these two. So thank you very much. We'll see in our next class on stochastic process to continue our discussion, okay? So I hope that is understood.